Happy Monday, 7Excel. So this week we are going to talk about our last topic for the school year. We are going to be talking about functions. We're going to start off with the basic of identifying functions. So what I want to preface this lesson with is the fact that right now we're going to be talking about functions. We are going to very lightly touch upon the different types of functions. Believe it or not, what you guys just did with linear equations, that is one type of function. That's called a linear function. There are other ones that you guys are going to learn about in algebra next year. There's quadratic functions, exponential functions. There's several other types of functions. So this year we are just going to primarily focus on linear functions. So what I want to give you guys is a quick analogy because a lot of seventh graders have trouble understanding functions. So before I go through this vocab piece, I want to give you an analogy to think about and keep in the back of your mind when I do go through this. So I want you guys to think about a vending machine. I know it's going to sound funny at first. Go with me. Okay. So think about a vending machine. You go to the vending machine and you have your heart set on Skittles. So you push the button to get Skittles and out comes Sour Patch Kids. At first, you probably would not be very happy. Okay, so you eat them. The next day you go back and you kind of enjoyed the Sour Patch Kids. So this time you want Sour Patch Kids. So you push the Skittles button because you think you're going to get Sour Patch Kids. Sour Patch Kids. And out comes Skittles. Okay, so what we're going to call this is called a broken function. Okay, this vending machine is broken. This would be considered not a function. It's not functioning properly. Okay, so functions are kind of like a machine. Okay, here is an input. I'm pushing Skittles button, and on 2 different days, 2 different candies came out. Same concept with a soda machine. If you were going to go to a vending machine for a soda and you pushed the Coke button, okay, and out came a Sprite, you wouldn't be a happy camper at first because you were expecting a Coke. So you go back the next day and you push the Coke button, and this time it produces you a Coke. Okay, this is not a function. Okay, so I want to give you one more, so that hopefully will give you a little bit of analogy of not a function. So let me give you an example of another function. So if you go to a vending machine and you have Swedish fish. So you push the button for Swedish fish and it produces and gives you Swedish fish. Okay, so far so good. Now, that's a function. Okay, it's working. It gives you the proper candy. So I want to give you another piece to this. So how many of you have ever been to a vending machine where there are multiple Swedish fish buttons? So maybe you can push like B6 or D7 and they both would give you Swedish fish. So it can have another button for Swedish fish, and as long as it produces Swedish fish for you, what you push, then that's a function. So this is an example of a function. So if you go to a soda machine, okay, and you want a root beer, it produces a root beer. The next one down might be a Pepsi, and it produces a Pepsi if you push that button. Then there might be another button down below. There might be 2 Pepsi buttons. So if this is a function, what does it have to do? It has to produce you a Pepsi. If it did not, then it would not be a function. So these are 2 examples, and I can throw up another one in here if you want it, if there was a Hershey bar in here. It would have to produce you a Hershey bar in order for this to be a function. So yes, this is functioning properly. Think about it like that. So that's just a quick little analogy that I want you to keep in the back of your mind. And I'll try to keep referencing that as we go through these notes. So let's go through a couple of vocab pieces here. So what are functions exactly? So remember, there are multiple types of functions, okay? We are going to focus on some linear functions here in the beginning. So function is a rule that assigns each input exactly one output. And what I want to make clear, depending on what we can have functions in tables or ordered pairs, as you can kind of see down here. We can have them on graphs. We know what those look like. And we can have them on mapping. I'll show you exactly what mapping is in just a few minutes. So input and output are just words that are standing for X value and Y value. Sometimes you'll see the words domain and range, okay? So the kind of clue that I always give seventh graders is input is your X value, output is your Y value, okay? Domain is your X value, range is your Y value. I put these in alphabetical order. D comes before R in the alphabet, X comes before Y. So domain is with your X value, I comes before O, input goes with X, if that kind of helps you memorize those. O goes with Y. Output is your Y value, range is your Y value. So maybe make an index card for functions here. Functions occur when every X value is associated with exactly one Y value. Okay? So there's different ways we can look at functions, and there's different ways that we're going to test each of these things to see if they're a function. So to test whether or not a table or a set of ordered pairs represents a function, we're going to look to see if each input or X value or domain, any of those words mean all three of those words represent the same thing, has exactly one output, domain, or range, or Y value. Okay, so I'll get into examples and this will make a little bit more sense. I know it's abstract right now. So graphs, what will graphs of functions look like? If a graph represents a function, it should be able to pass something called a vertical line test. Okay, remember, think about the vertical jump. How high can you go? So vertical up and down. This means that any vertical line drawn on a graph should intersect the graph at exactly one and only one point. All right, last piece is mapping, okay? I'll show you real quick. What mapping looks like down here this is mapping. So on a map here, each X value, okay, input, output, each X value must connect to only one Y value, input, output. Okay, that's what I mean by that. Make sure there isn't more than one arrow leaving an X value. So remember our analogy with the vending machine, okay? Make sure your X value is leaving not more than one. You don't want it to go to two different types of sodas. You'll never know which one you get. That's a broken function. Okay, so let's determine whether or not the following representations are functions. And we're just going to kind of talk about why they're either a function or not a function. Okay, so on a table here, okay, we have our X. These are our inputs. And our Y values, these are our outputs, domain and range. Okay, so we're going to look each of these inputs, okay, must have its own output. So -2 produces 7. -1 produces 1. 0 produces -1. 1 produces 1. 2 produces 7. So this is an example. So I'm going to bring this back to the analogy I gave you. So if -2 represents Sprite, then you get out Sprite. If -1 represents Diet Pepsi, then you get out Diet Pepsi. If 0 represents orange soda, then you get out orange soda. So this one is just another, because it produces to 1 as well. This is just another Diet Pepsi button. So this is a Diet Pepsi. It's going to produce you a Diet Pepsi button. And we'll say this one is root beer. This produces, nope, this is another one of the Sprites, because look at what it produces. They both go to 7. So that's our Sprite. So there's 2 different Sprite buttons here. There's 2 different Diet Pepsi buttons. Okay, as long as they're the same button here, so as long as every one of these X values has its own Y value, then yes, this is a function. Why? Because each of these X values has one and only one Y value. Okay, so let's take a look at number 2. So this is an example of ordered pairs. So where do we want to look again? We want to look at our inputs, or our X values, which are these numbers in ordered pairs. Okay, do we have our own, does everybody have their own input? Well, I noticed that these 2 ordered pair have the same input. Do they go to different outputs? The answer is yes. So if I go back to my analogy again of my vending machine. So if you push Skittles button, if -2 is Skittles, and you get out Sour Patch Kids here, and you push Skittles over here, but you get out Skittles here, that's not a function. It's producing 2 different quantities for the same X value. So this is not a function. Why? Because the input -2 has 2 different outputs, 1 and 8. Okay? Number 3, 4 and 5 are all examples of graphs. Okay? So remember, when we're looking at graphs, it has to pass the vertical line test. And that is a valid reason as to how you determine whether it's a function or not. And that's what is acceptable on the Algebra Regents as well when you guys take that next year. So the vertical line test is a valid reason. So you can say yes or no, it's a function or not a function. And it is a function if it passes the vertical line test. It's not a function if it does not pass the vertical line test. So we can draw a vertical line anywhere on this graph, and it can only hit the graph once. So if I draw one there, it hits it once. If I draw one right here on the y-axis, it hits the graph once. Right here, it hits the graph once. So yes, this is a function. And what's my reasoning? It passes the vertical line test. Okay? Graph 4. I'm going to draw a vertical line test, and look at how many times this hit the graph. This hit the graph 3 different times. So no, this is not a function. It does not pass the vertical line test. Okay. let me explain back and let me link these two together for you for a second. So if I come up with ordered pairs or coordinate pairs that make sense for this line. So we'll say this is -1, 1. That's -1, 3. And this bottom point would be, say, -1, -4. If you take a look, each of these inputs have a different output, okay? If you push Sprite here and it produces Pepsi, you push Sprite on this Sprite button and it produces Sprite, and you push Sprite on this button and it produces grape soda, there is something severely wrong with that vending machine, okay? That is not functioning properly. Okay, take a look at graph number 5. This is a linear equation. These ones are not, by the way, okay? These are quadratic equations. You'll learn about those in algebra. You guys know about linear equations. Does this pass the vertical line test? So if I draw a vertical line anywhere on this graph, does it only hit it once on each line? The answer is yes here. So yes, this is a function. Why? It passes the, I'm going to abbreviate for time purposes, vertical line test. Okay, last two examples here on number 6 and number 7. So these are called mapping diagrams, okay? And remember, mapping is the same concept. You can write them as ordered pairs. A lot of kids prefer to at the beginning until they kind of get the hang of it. Each x value must connect to only one y value, just like your ordered pairs up here, just like as if you produced it into a table. This is the same concept, it's just a different visual. So 0 goes to 5, 1 goes to 5, 2 goes to 5, 3 goes to 5. Some kids want to get tricked on this because they're like, oh, like all goes to the same. Well, let's write it in ordered pairs for a second. Okay, you could also write it in a table. Okay, so these inputs, x values, all have their own y value. And this is, believe it or not, yes, this is a function. Okay, this just means that they have 4 different, say, Pepsi buttons. Okay, they're all going to produce Pepsi though. And that's what you want. Okay, if this says Pepsi, it produces Pepsi. If this one says Pepsi, that says Pepsi. It produces Pepsi. If this is Pepsi, produces Pepsi. If this is Pepsi, it produces Pepsi. Okay, so this is just 4 different buttons. So every input, every x value has to have its own y value. Does that make sense? Now let's look at an example here. So 3 maps to -2, 1 maps to 0, 0 maps to -1, and 0 maps to 0. Okay, if you have a hard time looking at mapping, okay, you can write them in order. You can write them in ordered pairs. Anybody see not a function here? This is not a function. Why? Because right here, 0 goes to -1 and 0 also goes to 0. Making that analogy. If you push the Hershey bar button and this time it produces a Hershey bar, but you push the Hershey bar button down here and it produces a Butterfinger, you're not going to be happy, or you're not going to get what you expected. Okay, so this example is not a function. Every x value doesn't have its own y value. It has this one and it has this one. It does not have its own y value. Okay, so last piece to today's lesson. So in an equation, when we write them as an equation represents a function if every input x will only result in one output, your y. What you can do is you can substitute various input values, so x values, to see if the equation represents a function. So I want to just look at 3 equations now. So we're going to test different input values to determine if the following equations represent functions. This example, y equals x squared, okay? So in here, I'm going to give you one quick example, and I think you're going to quickly catch on to equations. If we use 1 as our x value, 1 squared is equal to 1 times 1, which is 1. So that works. Now, what if x is negative 1? Negative 1 squared is negative 1 times negative 1. Negative times a negative is a positive, and 1 times 1 is still 1. So is negative 1 squared equal to 1? The answer is yes. So basically, when you plug in anything squared, is that going to equal the y value? So I'll give you one more example. So we'll just use 5. 5 squared is equal to 25. Is 25 equal to 25? Yes. Okay. So yes, this is a function. Okay. Because every input results in one output. Negative 1 has 1. If I put that in as an ordered pair, it might help you see that. We inputted negative 1 and we got out 1. We inputted 1 and we got out 1. We inputted 5 and we got out 25. Every example of x produces its own y value. Okay? Now let's take a look at number 7's equation. Okay, this is y squared equals x. So if my x value here is 4, what number could we square to get 4? The first thing you probably think of is 2 squared. 2 times 2 gives you 4, which is true. Is there any other number that you could square to get 4 as well? Any different number? The answer is also yes here. Take a peek. Let me challenge you to think about this. What about what's negative 2 squared? That would be negative 2 times negative 2. That is positive 4. So right there, your input is 4. Your output could be negative 2. Here, my input is 4 and my output is 2. So if you think about that, that would be not a function. So this is no, not a function, because the x value of 4 has 2 different outputs. Okay? The last example here. X squared plus y squared equals 25. So this one kind of looks tricky, but so what I want to explain first is how could we square numbers and add the sum to give me 25. So the numbers that work to add up to 25 are 3 squared plus 4 squared. So let me show you the first example here. So 3 squared plus 4 squared is 25. So 3 squared is 9. 3 times 3 is 9. 4 squared is 16. 9 plus 16 is 25. So far, our input and output are 3 and 4. So is there a way to prove that this is not a function? Okay, so that means if I plugged in 3, it'd have to come up with a different output. So I'm going to plug in 3 again. So 3 squared we know is 9. So I know 9 plus the only number that I can add to 9 to get me 25 is 16. So is there another way to get 16 without 4? So kind of like I was showing you back here, negative 4 squared is negative 4 times negative 4. Negative times a negative is a positive. Therefore, that would also give me 25. So the input of 3 in the output of -4 also work, but that makes this not a function. Why? Because this 3 has 2 different outputs. You push Pepsi, you get Pepsi at first. You push Pepsi and you get Diet Pepsi. Somebody might not be happy if they don't like diet soda. Does that make sense? Okay, so that's equations. So it's sometimes easiest just kind of check to see. What you're going to notice is, if you notice from this pattern, y equals something tends to be an A-OK function. Anytime you have y squared in your function, not a function. Okay, so what I want you to do right now is I just want you to answer number 9. Is number 9 a function? Yes or no? Is number 10 a function? Is number 11 a function? Is number 12 a function? Is number 13 a function? Is number 14 a function? Is number 15 a function? Okay, have a great rest of your day. That is our lesson on intro or identifying functions.